Okay, hello, welcome to the last third of the course. So, this third of the course is the chill third of the course. So we're pretty much done all the hard stuff. So, for the last third of the course, feel free if you want to review anything we've seen before, or if you try and apply, making threads or processes to your solutions or other projects, we can discuss that. Do all sorts of fun stuff. I'm also not opposed to going over Lab 3 if people want me to go over Lab 3. A fun thing could be, throwing it out there, someone that doesn't understand it can or their solution might not work, can just tell me to review their code, and I'll review their code in the class and compare it with the solution. We'll have all types of fun, and if you do volunteer for that, I will not tell anyone who you are. So probably don't want to do that. All right, so yeah, I might have to go over Lab 5 stuff, so I'll release Lab 5 and hopefully grade Lab 3 after this on the commute home. But for today, let's talk about disk. And to justify my decision of cutting some content, who has ever used a hard drive that spins? You know, the spinning thing that goes woo and whirls? 1, 2, 3, 4. All right, any other spinning diskers? So not that many, so like over half of you have never used a magnetic hard drive. So yeah, I'm just cutting that content from the course because no one really cares how a magnetic hard drive works, unless you're like hoarding a bunch of movies or something like that, in which case they would be useful. But I cut that, and we will talk about solid state drives. So they're the more modern thing. They use transistors like RAM. They're not magnetic. They don't spin. They don't do anything like that. So there's no moving parts. You can't jostle them like, the first generation iPhones were magnetic spinning disks. So if you ran too hard, they would skip and do all sorts of weird stuff, and you don't want that. So SSDs or solid state disks, no moving parts or other weird physical limitations, because as you might imagine, if you have a spinning disk, well, you have to wait for it to spin. It spins at a certain rate, who cares? We use SSDs. They have higher throughput. They have good random access, so you can access any page or any byte you want, and you'll get it at pretty much the same speed. They're energy efficient. They have better space density. The only cons is that they're more expensive. They have a limited endurance, so you might have not known this, but if you buy an SSD, it's only rated for a certain number of writes to it, and then after that, it wears out and can't store any information anymore. There's also some weird peculiar behaviors with that we will go into today, and they're a bit more complicated to write drivers for. Thankfully, we won't be writing any drivers, but we'll talk about what some of those complications could be, because they kind of seep into operating system design and things that you have to think about. So SSDs also contain pages. And again, pages are just fixed size blocks of memory. So SSDs also have pages, just like the virtual memory system also deals with pages. So they're organized a bit differently. There's a big hierarchy of this. So in the green here, those are pages, and those are blocks of typically 4 kilobytes, so 4,096 bytes at a time. And those are organized in blocks. So a page will live in a block, and typically there'll be like 8 or 16 pages in a block. And then within the block, multiple blocks will live on a plane, and then it'll all live in a die that you can actually visually see if you open up an SSD and start playing around with it. So that's a bit how they're organized. For this purposes of this course, we only care about pages and blocks. Yep.
So even the page is 4096 bytes?
Yeah.
Does that have anything to do with why, like, in C, buffers are typically made to be 4096 bytes?
So they're kind of related. They nicely fit up with pages in our virtual memory subsystem, and they just made it because it matches and everything lines up. But the original 4 kilobyte page size was from the virtual memory system. All right, so using SSDs and NAND and flash, whatever, are much faster than HDDs. There's a typo on there I need to fix, because They're not spinning or anything like that. So pages typically line up with exactly what we have from our virtual memory system. So 4 kilobytes, and then like some timing metrics. So reading a page is like 10 microseconds. Writing a page is typically slower. It's like 100 microseconds. And then erasing a block is like 1 millisecond. And you'll notice here that it says erasing a block, which is a bit weird because it doesn't say erasing a page. So the weird thing about SSDs is you can only erase blocks at a time, not individual pages. And remember, going back here, there are multiple pages per block. So if you erase a block, you wipe out, 6 or 8, 16, whatever pages, and that's what makes things difficult. And that's just a way the hardware works. Yep. Oh, that was the question? Yeah, so it's designed that way due to physics I don't understand. So some of you might understand physics of an SSD later. I decided not to care about it, but if you really care about it, there's a reason to that madness. I just don't know what it is, some physical limitation, something like that. But if we care about programming, well, you can only read complete pages. And another weird thing is I can't just write to any page I want. I can only write to freshly erased pages. So that adds another layer of complexity for us if you are managing the SSDs. So again, remember, erasing is done per block. Blocks can actually have more pages than the diagram shows, so it can actually have 125 or 128 pages or 256 pages. And again, the entire block needs to be erased before you can write it, and you're not allowed to rewrite it after you write it one time. And writing is really, really slow, especially if it needs to use a new block. You can imagine that you might be in a scenario where you want to write to one page on a block, and that block has like 250 or 227 pages filled of data. So if you want to write to that and it's not freshly erased, well, what you might have to do is just erase a random block and then copy every single page to the new block and then write your new page to it, which, as you can kind of see, is kind of annoying. So the OS, if you're doing that, you have to manage all that and follow those rules. And the operating system's job is to help that hardware be as performant as possible. So you want to try and minimize the amounts of blocks you're erasing and moving content and all of that fun stuff. So SSDs will need to garbage collect blocks. So that's why I was just kind of alluding to there, that if you need to write some new data and you're not allowed, it's already been written before, well, you have to move pages to a new block, which of course would also have to be freshly erased. So there may be some overhead there. We have to wait for the block to be erased, and then you have to write over any pages you want to copy, so on and so forth. And also, the disk controller is generally pretty dumb. So you might write to a page, and then you might delete the file. You would know you've deleted the file, but actually on the disk, that data is still there. The operating system is just not going to use it anymore. So the disk won't do anything special about it. And also that's why, one of the reasons why if you delete a file, people can just recover it if they know what to do, because generally whenever you delete something, it doesn't actually delete it, it just doesn't use it anymore. So that's why, if you need to shred some FBI documents or something like that, you should just write random crap over it, so you just obliterate the data. So since the SSD hardware doesn't know what blocks or what pages or what blocks may still be alive, then the operating system has to help it out and tell it which ones aren't used, and therefore the operating system would need to keep track of it. So there is something called a trim command, and that informs an SSD a block is unused, because otherwise it wouldn't know whether or not the pages on the block are used or not. So the trim command is a way to tell the SSD hardware, hey, I'm not actually going to use that block anymore. And then the SSD hardware itself will go ahead and erase that block whenever it has free time and it's otherwise idle, so you don't have to get that overhead, and that will therefore speed up everything. So far, we've only been talking about single devices too, which is kind of boring. Sometimes it's jokingly referred to as a single large expensive disk. And if you really care about your data, generally you don't want to do something like this. So if all your homeworks are on one hard drive and that hard drive dies, well, you are now completely screwed. So generally, if you care about your data, you don't do that. So that's a single point of failure. So the opposite of a single large expensive disk is a redundant array of independent disks, implying that they're probably cheaper. So instead of buying one disk and you write your data to that, you buy multiple disks and you distribute your data across the different disks. And because you can distribute your data across different disks, well, you have a bunch of different design options you can use depending on how much you care about that data. So you can use redundancy, and all redundancy means is I have multiple copies of something. So I can use redundancy to prevent data loss, or I could also use redundancy, the fact that there's multiple copies of a file, to also increase the throughput of all of my disks working together over just a single disk. So the easiest one is called RAID 0, and it is called a stripe volume. Typically, it will take all of your data and organize it into stripes, which will be like 128 kilobytes or 256 kilobytes, and they're distributed over the disks. So this 0 here would have like the first 128 kilobytes of a file A1, and then the next 128 kilobytes would be on the stripe A2, and then it would just alternate back and forth between the two drives. So essentially, half the file is on one drive and half the file is on another drive. So in this case, we don't have any redundancy, so we still have one copy of this file A. It's just half of it is on one disk and half of it is on another disk. So why would I want to do this? Well, if you stripe data across all the disks, you get faster access time. So now instead of reading one file from one disk, well, I can speed it up by a factor of 2 in this case. So if my bottleneck is a disk because they're slow, well, instead of reading one file from one disk, I read half from one disk and then the other half of a file from another disk, and therefore it's twice as fast. So any questions about that? Nope. Okay, so this extends, I can do this with however many drives I want. So I could do it with 4 drives. So instead of splitting, all your data up into just half on one, half on two, well, if you have 4 drives, it's like a quarter, a quarter, a quarter, and a quarter. So if you want to read, then you read a quarter from each drive, and it's about 4 times as fast. It gives you that fast parallel access. But now you are in the unfortunate situation where before you had a single point of failure and now you have multiple points of failure. Because if I go back to this, I don't have 2 copies of the file. I have half on one drive, half on the other. So if one of these drives dies, I lose half of the file and I can't recover the other half of it. It's just corrupted, it's useless. I can't use it anymore. And it gets worse if I have 4 drives. If one of those drives dies, I lose all my information. But the nice thing about this is it's really, really fast. So if you really care about performance and you don't care about the integrity of your data, like say a game or something like that, where yeah, my hard drive gets corrupted, whatever, I'll just re-download it, I don't really care, then you might want to use something like this. So it's typically only used for performance. The other extreme is something called RAID 1, which is a mirror across all the disks. And what a mirror implies is it's like an actual mirror. So everything is the exact same as one another. So if this file was split up over 4 little chunks, like A1, 2, 3, and 4, well, both hard drives are going to have a copy of each of those chunks. So now, if one of these drives dies, well, it doesn't matter because it was an exact copy of the other drive, and I haven't lost any data. So you can actually recover from this. So in general, this scales up when you talk about RAID 1. that every disk is just an exact copy of all the other disks. So if I had 4 in this case, all 4 would be exact copies of each other. So why you want to do this? Well, maybe you really, really care about your data. So as long as one of those disks is still alive, you have not lost any data, which is great. And it also gives you good read performance. So even though we have the file split up over, or 2 copies of the file on each hard drive, I can still get the read performance benefits of RAID 0 because I could read, say, A1 and A3 from disk 0, then I could read A2 and A4 from disk 1. So I can still read half the file from one drive and half the file from the other drive and get, like in this case, 2 times more read performance. But my write performance is the same as a single disk because if I need to write this file, well, I have to write it to every single disk. I could write it to every single disk in parallel, theoretically, so it would be just as fast as one disk and I get no speed improvement whatsoever, but it also doesn't go that much, it doesn't really go slower. So this has a really, really high cost for redundancy, so I'm wasting an entire drive, or if I have multiple things in RAID 1, then I'm essentially just wasting drive space, unless I really, really care about read performance and really, really care about my data. But you don't get any benefit to write performance. So any questions about RAID 1? Cool. All right, so RAID 4, you'll notice we have skipped some numbers. So RAID 2 and 3 are just some weird mistakes in the past that we will not go over. And in fact, RAID 4 is also a bad idea that is never going to be used, but we'll go over it very quickly because it will help us understand RAID 5. So RAID 4 introduces something called parity. So it's the same idea as RAID 0, where we stripe the data over the disks. But in this case, we have a dedicated kind of backup disk or a parity disk. And the property of that parity disk is as long as we have some parity information, if one of those disks dies, we can reconstruct whatever data got lost. And all the parity is an XOR calculation. So we can see that real quick. So say we have 4 drives and we have disk 0, 1, 2, 3, and on 3 we have what is called some parity information. So an XORG will essentially, if you don't want to go into the details of XORG, the easiest way to think of it for binary numbers is it will tell you whether or not the result of adding everything together is even or odd. So if you XOR everything together and it's 0, it means it's even. If you XOR everything together and it's 1, it means the sum of everything is odd. If you want to think of it that way, typically I think that's an easier way to think about it. So the idea behind the parity bit is it's an XOR of everything. So if on disk 1, let's say we have a 1, 0, 1, and say we have 0, 1, 1, 1, 0, 0. So say this is the data on all my drives. Well, for each bit across for all the bits across the drives, I calculate a parity, which is just an XOR of everything. So if I XOR 1, 0, 1, well, if I want to take the shortcut, that's an even number. So if I XOR all of them together, that's a 0, aka it is the sum of all of them is even, if I want to think of it that way. Then if I XOR all these bits together, well, it's the same idea. It is even. And then if I XOR together 1, 0, 0, well, all of them together XORed is a 1, or otherwise I can think of it as odd. So now the fun property about this is I have some more information that if one of these disks dies without knowing any of the information that was on it, I can reconstruct it. So let's just assume, so remember 0, 1, 0 and we'll in disk 1, and we will figure it out as if not knowing anything about it. So say this disk dies. So now we lost all of that information. But because we have some parity information, some extra information, we can actually figure out or deduce what bit was there that we lost. So the idea here is that drive dies, you go to the store, you buy another one, and you say, please reconstruct my data, I don't want to lose anything. So we're basically solving an equation here, so it's like, so 1 plus 1 is even, and then it's like plus either a 0 or a 1 gives us something even. So if I say this information lost was a 1, well, this doesn't make sense anymore according to the parity bit, because it says if I add up 0, 1, 2, which is 3, it says I should get an even result at the end, but right now it's odd. So clearly what I lost was not a 1, it was a 0. So I reconstruct a 0, and then you do the same thing with the other column. So I have a 0 and a 1, so sum together as 1 is odd, and then plus 0 or 1 equals something even. So this has to be a 1 because 1 plus needs to add to 1 to make something even, right? If it was a 0, it would be odd, and then it would not agree with this. And then similarly for the last column, well, I have a 1 and a 0 add together, that's a 1, and I know if I add my missing bit, it should produce an odd result, so therefore this number has to be a 0. So we can reconstruct that drive we lost just by using that parity information and looking at all the other information, and we can go backwards and figure out what information we lost. So any questions about that? Okay, so that's the whole idea behind RAID 4. So no matter what, if we lose one disk, then we're good. So if we argue about how much space we can actually use for the disks, well, essentially, because all the data is striped across the disk, I can use all the data minus that disk 3 there. There's one disk reserved for parity, so I can't use that for any of my useful information, so it won't store any of your files. It's just storing that XOR calculation. It's just full of XOR calculations of all the drives, and that's it. So with this too, you also need at least 3 drives to be worthwhile or to even be possible to use. So you need at least 3 drives, and 1 disk is going to be wasted for that, storing all that parity information. So pros here is we're going to get a performance boost over using a single disk, of course. So we get n-1 times the performance boost, because if we remove the parity disk, it essentially looks exactly like our striped example. So it's just exactly like our striped example, but we have 1 disk we're using for parity. And the nice thing about it is, well, now we have some redundancy. If one of my disks dries, I don't lose any of my precious data, because I can go buy another one, stick it in there, and rebuild it, and it will get all my data back, and I will be happy as a clam. The bad thing about this is the write performance really suffers. So every write has to write to that parity disk. So because these are striped, well, if you're using a bunch of like little small files, well, if I touch, say I just touch A1 here on disk 0, and I touch B2 on disk 1, and I touch C3 on disk 2, well, those are 3 accesses to different disks that can all be independent, but this disk 3 would need to calculate a parity bit for A, B, and C. So it's going to have to do 3 times the work, which isn't that great. So there's kind of a little bit of a bottleneck here on that disk, because whatever you do to any disk, you're going to have to touch that parity disk, which is not going to be terribly good for performance. So that is where RAID 5 comes in. So RAID 5 is literally the exact same idea as RAID 4, except it removes that bottleneck on a single drive. So now instead of having one drive have parity information for all the other drives, it's distributed across all the disks. So in this case, disk 3 only has the parity information for A, disk 2 only has the parity information for B, disk 1 has the parity information for C, and disk 0 has the parity information for D. So each of them, you just distribute the parity across all of them, so there's no one bottleneck on any one individual drive. So any questions about that? Same idea as RAID 4, but it distributes it, gets rid of that bottleneck. So that's why no one ever uses RAID 4, because it's the same idea as this, but this is just better in every respect because it doesn't have that bottleneck. So all the same pros as RAID 4, and our write performance is also improved a bit too because we no longer have that bottleneck on that single parity drive. So if I have all those writes, well, all the writes don't have to wait to write to a single disk. It's distributed across all of them. So your write performance will be a bit better. Yep.
So does accessing like A1 and BP like less computationally expensive than A1 and B3 like we do in RAID 4?
Sorry?
Like in RAID 4,
Mm-hmm.
we have to access 2 disks, but now in RAID 5, we have to access the same disk twice, and that's less expensive.
Yeah, well, the idea is that it just be distributed across all of them. So like you can come up with cases where one disk will still be kind of a bottleneck, but it's just the average, it will be distributed across all of them. So if I'm writing to all the files, well, it's not concentrated on one single disk I'm waiting for. It just improves the average time. So it doesn't reduce the number of writes or anything, it just makes it distributed a bit more. So you can still come up with cases where this still has an excess of writes, but in general, on average, it gets better. All right, so RAID 6 is the same thing, except it adds another parity calculation. So instead of just a single parity, there are 2 sources of parity. So we now have P, which is our normal parity information, and also a Q, which is another parity calculation. So we have 2 calculations now, or 2 equations. And the way this works is it's the same idea. It just distributes those parity bits across all the disks. So for example, disk 3 has the P of A and the Q of A, and disk 2 has B's P, and disk 3 has B's Q. So it's the same idea. We just have another redundancy calculation. It's just distributed. Yep.
So P and Q aren't the same?
No. So P and Q aren't the same. So P would just be the XOR calculation, like that equation. The Q calculation is going to be a bit more involved. So we won't go into the details of what that calculation is. It gets into some fairly advanced math, if anyone has ever heard of Galois fields, I think, something like that. So it's basically, it just goes down to like your distributed numbers course. It's just another equation. So you can solve for 2 unknowns now. So we don't have to worry about the actual parity calculation. You can just think of it in terms of like discrete math or whatever, where we have another equation so we can solve up to another unknown. So it's the same idea here, but we just have an extra parity calculation. So now we can tolerate 2 disks dying because we have 2 equations. So one's easy to understand, which is just straight XOR. The other one, if you're more interested in it, you can look it up. Like I said, it's more involved, but it's perfectly doable. So now we have essentially 2 disks of parity because we have 2 other equations, and this requires at least 4 drives. And for your usable space, well, 2 drives are essentially used for parity information. One's for the parity of Q, one's for the parity of P. Yep.
And you can reconstruct any 2 drives, including if one of them is the parity drive, right?
Yes. Yeah, you can reconstruct any 2 drives. So the write performance is going to be slightly less because we have to do another parity calculation, and rebuilding it might be a bit slower because it's 2 calculations, but yes, you can redo any of the ones you want. Yep.
Why does it require at least 4 drives if the parity is distributed along the different drives anyway?
So if you just have 3, that's like 1 drive for useful information and then 2 drives with parity information. So at that point, you may as well just use a RAID 1 and just have a mirror because it's the same thing. So you're just kind of wasting space at that point. So you want at least 4 drives for this. Yep.
How often do these drives fail? Like, is this just a general failsafe for like really important information, or is this with the standard SSD kind of system?
So the question is how often drives fail. So drives fail a lot. So typically with these RAID configurations, you use a spinning magnetic disk. So that's like in the big warehouses and stuff like that. And if you run a big data center, these things fail. I think the average failure rate is like 5% a year. So if you're running like a Google data center, these are going to die constantly. Like drives, it's not a question of if a drive will die, it's just when. And they die all the time. Yep.
Is the recovery time fast enough that it's not likely that one fails, one other one is also has already failed?
Yeah, so that's a funny story. So as part of my grad studies, I knew about this. I had my work on a RAID 5, so I could tolerate a drive failure, no problem, right? So inevitably, when I'm about to finish up grad school, one of my drives dies. And I'm like, okay, well, I can still access all my files, no problem. And while I am too lazy to go out into the store to buy another one to reconstruct it, another one dies. So since I had a RAID 5, did I lose data? Yeah. So I had a RAID 5, 2 drives failed because I didn't replace one in time. Typically, they will go at the same time because typically when you buy them all at the same time. So their failure characteristics will probably be fairly similar. So what you typically want to do is buy the same brand of drives, but from different stores. Try and distribute it a bit so they won't fail at the same time. Luckily for me, one that started to fail was still not too failing, so I ran to the store, bought 2 drives, and it recovered most of it. So I was lucky, but don't be like me, and don't do that, because if one drive fails, that means you are like living on the edge. Another one's probably going to fail, so you may as well go fix it. So, and yeah, these things, depending on how fast they are, like RAID 5 and RAID 6, take a long time to rebuild. So recalculating that for like terabytes of data or something like that takes a long time, like on the order of days. So you have to wait a few days. You can't really use it. You have to wait for it to rebuild. So that's another consideration with this. And there's also what we didn't talk about, but we should talk about. So there is a combination of doing RAID 0 and RAID 1. So this has no redundancy whatsoever. It just splits half the file on one, half the file on another. But you can do this in like a tiered configuration. So you can do something that's called a RAID 1 plus 0, or sometimes it's called a RAID 10, where essentially you have 2 copies of this. So you have 4 drives, and you have one that looks exactly like this, where half is on one drive and half is on another drive. And then you have an exact mirror of this. So you have another 2 drives that have half of the same information. And that way, you can only use half the space because you have a mirror, an exact mirror, but you don't have any parity calculations. So if a drive dies, well, reconstructing it is really, really fast because all you have to do is copy the data. You don't have to do any calculations whatsoever. You just copy the data. And each of the drives has a mirrored pair. So you only lose data in the event you're really unlucky. So you'll lose data if both pairs die at the same time. But as long as you have one in each pair, you can tolerate some failures. So like if I have 8 drives, well, I would have a mirror, and then everything would have, 4 different pairs of stuff. So in the best case, I could lose up to 4 drives and not lose any data if it was a unique pair or one of the unique pairs for each of the drives that died. Or I could get really unlucky and then just a pair together dies and then I lose a bunch of data. So those are other ways to go about it. Typically, if you don't, RAID 1 plus 0 is actually typically more used just because of that reconstruction time, because it's a lot faster than recalculating parity information. You lose a bit more space, but if something fails, typically you want to get back up and running as fast as possible, so people use that. And I've actually switched my stuff over to use that, so I don't have that same situation again, because yeah, it's not good. All right, any other questions? Yeah, basically don't do what I did. All right, so these are disks, and they are part of our persistence of an operating system. So we'll go into more details later. We explored SSDs and RAID, so these are, again, are your non-volatile storage. So whenever you reboot your computer, all the information is going to be there. It's going to be great. So we saw SSDs, they're more like RAM, except, well, they survive a reboot, and they are accessed in pages and differently blocks, and they have a lot of very weird rules. Mostly being that you can only erase in blocks at a time, and you can only write to a freshly erased page. So that comes with a bunch of challenges if you get into the nitty-gritty details. Because of that, SSDs need to work with the operating system to get the best performance. So like that trim command to inform the actual SSD hardware that, hey, I'm now no longer using this block. You're free to erase it when you're otherwise idle. And then we saw a bunch of RAID. So they allow you to tolerate failures, improve performance using multiple disks, and that's what any data center is going to use. So, yep.
So is it common for SSDs to use RAID or like a RAID above RAID 0?
Yeah, so SSDs can use, especially like the cheaper ones. People are buying them and putting them in RAIDs now. But most people do a RAID for spinning magnetic disks just because they're cheaper. And we'll talk more about different storage mediums when we go on.
Because I'm wondering if I should like set this up for my SSD now because I don't think it has RAID.
Yeah, all your laptops will not have this.
Oh.
So that's why you should push your code to the server often. And then if your laptop dies, well, it's kind of like you have a RAID 1 because the mirror is the server and you don't have to worry about it. So yeah, but if you're also like a data hoarder like I am, then you might want to know this stuff too. And essentially, don't do what I did with my RAID 5 when drive dies and you just don't do anything about it. All right, any other questions? We can wrap up early. Told you, chill third of the semester. Well,
Does that mean the labs are easier?
So Lab 5, we'll see. I'm going to release it right after this. You guys can read it and tell me what you think. I might have to go over virtual memory again. But yeah, it'll be virtual memory. But just remember, phone for you. We're all in this together.